Hello, my name's Nicholas. I am a programming language and concurrency researcher at Imperial College. So you'll be getting a slightly different perspective of Go from me. And today I'm here to talk about a deadlock detector we've developed for Go based on our research. So let's start with Go and concurrency. So Go is a very interesting programming language, and it's got a very unique approach towards concurrency. So don't communicate by sharing memory. Share memory by communicating. Who has heard this before? Very good. I see most of the hands up. And so this actually captures the concurrency model of Go very well, because instead of using threads and logs for doing high-level concurrency like most other programming languages or libraries, in Go we have message passing over channels. And these messages are used for coordinating and synchronizing different Go routines. So that's how we get our concurrency. And the model is said to be inspired by Tony Hoare's communicating sequential processes, or CSP, which I'll elaborate a little bit more later. But for developers, what's important is that we have an expressive and a message passing based concurrency model that developers can use to write concurrent programs. So we're talking about concurrency, so let's not try not to get too carried away. So concurrency is complicated, no doubt about that. And unless you're a really, really good programmer where you can write perfect code every time you write concurrent code, there ought to be some concurrency bugs. And with concurrency bugs are hard to track down and let alone fix. So a big part of our research is to try and help developers by helping to avoid concurrency bugs as much as possible so that we don't actually encounter them in, let's say, runtime. But first of all, what do I mean by concurrency bugs? So here is an example. I've got a very simple program, sender. We've got two functions. One is a sender, which sends a message to a channel. And we've got a receiver, which receives a message and then forwards the message to another channel. Very simple, right? And then at the main function, we spawn 3 Go routines, 1 sender and 2 receivers. So something's strange going on in this program because we've got only 1 sender. Why do we have 2 receivers, and why are they trying to receive on the same channels? So a bit of luck. If we run this program, where it says, fatal error, all Go routines are asleep, deadlock. I think it's very obvious what's going on here. We've got a deadlock because all the Go routines are asleep or stuck. But let's go into a little bit more details and see why we get this deadlock. So let's look at how message passing works in Go. So you have a sender, you have a receiver. So the sender Go routine tries to send a message to a receiver through a channel. And then, because the receiver may not be ready, so the sender blocks the Go routine. So the Go routine goes to sleep and waits until the receiver is ready to ready to deliver the message. So imagine if you have a sender Go routine which tries to send a message, and you have a receiver that is not prepared to receive a message, like ever, then the sender Go routine is going to block forever, which may be fine. It's a wrong program, but it may be fine in some cases. Maybe the other Go routines will still continue to run, right? But if you have this to appear in all other Go routines as well, like all the Go routines are waiting for each other. So here is a very classic deadlock in the literature. So you have 2 Go routines trying to send a message to each other. So both of them have to receive, both of them have to send, but then you got the orders wrong. So both of them tries to start with receive. Nobody's sending anything, but both try to receive. So both of them block. So then the whole program gets stuck, and that's why you get a deadlock. Well, of course, to avoid deadlock, we just have to reverse this and say, well, if I have a send, I should have a receive, and if I have a receive, I should have a send, right? And so, well, we can fix this really easily. when you don't have other code in your program. And the same principle applies to other kinds of deadlocks. So of course, send and receive, you can get these kind of deadlocks. And another very common kind of deadlock you get with Go is if you range over a channel, and then so when you use the for loop to range over a channel, it tries to receive all the messages in the channel until the channel is closed. So if you've forgotten to close the channel, or if you've forgotten to put a message in the channel, then you also get a deadlock, because one of the threads will be waiting for something that's never going to happen. This sounds really, really simple, but turns out in practice it's very hard to really do. Well, why? Because of two main reasons. One, communication, you don't usually write communication code in isolation. You don't just have a program that just sends message. You want your program to do something, so you have to intertwine it with non-communicating code. So maybe you're calculating something, and then you want to send the result to a receiver, something like that. And well, then very simple. Then I just remove all the lines that are not communication. But that doesn't work very well either, because the program control flow isn't a straight line. You don't write a program that only do one thing and always does this thing. So you can't just remove the lines. It also has got other control flow, if then else, you've got loops and many other things. So the way we approach writing, avoiding deadlocks is actually very complicated. Well, but then Go has a deadlock detector, right? Anyone use this or anyone encounter this? Yes. So the deadlock detector in Go is a runtime detector, which means when you execute a program, when it sees a deadlock, it tells you, oh, there's a deadlock, and because there's a deadlock, I can't do anything. So kind of panics and say, oh, sorry, can't do anything. But it really is really simple. The idea behind the runtime detector is very simple. So the code in the bottom I've shown here, it comes from the Go runtime, and that's really what it is. It counts the number of Go routines that are currently unblocked and running. So as you can probably tell, if the total number of Go routines that are running are 0 and your program's not finished, then everybody got stuck. So of course you get a deadlock. Fair enough, but why do I need a new deadlock detector? Why can't we just use this? This is good. So let's say I have the same program as before. We didn't fix the bug, and we try to extend the program. We try to put one extra Go routine in the program and say, well, it just, it's concurrency, so I just spawn a new Go routine to do some long-running tasks. This could be a server process. It could be just polling something or anything. And it has nothing to do with communication at all. It's just a completely benign Go routine. So if we run this program, whoops. So as you can see, we still get this deadlock detected in the program, but it's only after when the work is finished, because every time the deadlock detector comes around and check if there's still running Go routines, yep, something's running, so there's no deadlock. But in reality, the deadlock that we've seen before with the senders and receivers are already there. It's still there. It's just waiting for the whole program to get stuck. And imagine if you have this other worker Go routine which is taking, 10 days to run before it finishes. You don't want to run your program in production 10 days and then suddenly, whoa, deadlock, and the whole web service crashes, right? And in the literature, this is sometimes called local deadlock, because not the whole program is stuck. So in the normal case, in the case where the deadlock detector detects something, it's called a global deadlock because everything is stuck. But here, it's isolated in some parts of the program, so it's called local deadlock. Well, so we set our mind out to build a better deadlock detector than the one that's already in Go. And what if we can detect a deadlock in a program without running it? So it doesn't depend on how long the program runs. We can just know whether there's a deadlock or not. And then, or we can if we can find local deadlocks as well, it will be really nice because that's what real deadlocks will happen. And of course, we wanted it to be goal-specific. So most of the deadlock detection are based on, in other programming languages, are based on locks and threads, and it's not quite the same as communication, even though you may say it's kind of equivalent. But we want it to be goal-specific. So how do we do that? So we developed a deadlock detector based on our research, and it's on GitHub, and you can download it and try it. It's a compile time deadlock detector. So instead of running a program, it actually allows you to detect a deadlock when you compile the program. And it helps prevent deadlocks, and most importantly, it's still an ongoing research, so you probably see more improvement over time. But so far, we've been able to analyze common concurrency patterns and 1 or 2 open source projects with up to a few hundred lines of code. Well, and how it works is it starts with the program source code. We analyze the Go source code, and we extract or we infer the communication model representing just the communication bits of the program. And then we check if the model can get stuck. If the program is stuck, or if the model is stuck, then we know that the communication in the program has problems, so the program has problem as well. But if the model doesn't get stuck, then we know this is likely okay. The reason I'm saying it's likely okay, it's not 100% okay, is because in static analysis, or when we analyze a program without executing it, there are often things that only happens at runtime, so maybe user input or something like that, that we cannot, we have to do some overestimation of assumptions. So we can't guarantee everything. So there ought to be false positives. But in general, the approach is that, well, if it's okay, then the source code likely okay. Right? So I'll spend the rest of my talk describing how we really detect deadlocks. But first of all, I wanted to talk about modeling concurrency, because this is where the real juice of our research is. It's about taking your program and having a very accurate representation of communication. And then we also wanted to use some established ideas to see how we can know whether there's a deadlock in the model. And well, who better to ask than pioneers of computer science and concurrency? So Tony Hoare is a researcher who's invented CSP. If you've read Effective Go and others, you probably know this name before. And he's also known for something like other important ideas like quicksort, Hoare logic, and many other inventions. And in around the same time Tony Hoare invented CSP in 1978, Robin Milner, yet another pioneer, came up with CCS, or Calculus of Communicating Systems. And then he followed it up later with PyCalculus. And of course, Robin Milner is also not just working in concurrency, he's also working in many other things like the ML programming language, LCF, and others. But collectively, the CSP, CCS, PyCalculus, these things are canonical models for communication. They're very similar. They try to solve the same problem, and collectively sometimes we call it process calculi, because because process calculi are formal models of communication. So we represent models of communication as an interaction between processes, or in this case, it's interactions of Go routines. Well, this is where Go's concurrency model comes from, and this is also where we build our deadlock detection technique on. And that's why it's very close to what you would do in Go. And so don't worry about this complicated figure in the bottom. It's not going to be in exams, but this is actually the whole syntax of asynchronous PyCalculus, so one of the process calculi. And as you can see, it's very succinct, it's very short. Even though it's so short, it still be able to represent all the important communication primitives in Go, like spawning Go routines, creating channels, sending, receiving, etc. Well, the problem with these models is it's a very succinct representation of communication, but then it doesn't really stop bad interactions from happening. So so it's like giving you a programming language. You can still shoot yourself in the foot if you do something stupid. But now that we have a very, very accurate model of communication, all we need is to check if the model is okay, whether the model is compatible with each other. And so we turn to another important idea in programming languages, which is types. As we know, Go is a type programming language, and it offers compile time static type checking. So basically, this is just asking the question whether, well, if a variable is compatible with a value. So I have a very simple example here. I'm assigning the value 42, which is an integer, to the variable x. Well, so we know that x is also an integer, so this assignment is okay. But if we try to assign the value hello, which is a string, to x, which is a string, then obviously this is not going to work. And if you try to run this, it actually says it's actually a compile error, because the type checking actually happens when you compile the program, and you don't need to run the program to know that, oh, that this type isn't right? But you may be wondering now, well, types, communication, what does that have to do with deadlocks and stuff? And so this comes to what my main research is about. My main research is what's called session types. And basically, it's a typing system for communication. And it originates from putting types on calculus. And all you need to know is it's asking the question whether a sender is compatible with a receiver. What do I mean by that? So we talk about compatibility here in terms of the communication structure. So on the left-hand side, we have two Go routines, and one of which is receiving and then sending to a channel, and then the other is sending to and then receiving from a channel. So the two structure of the communication are compatible. They're okay. So when you send, you have a receive ready. And then on the right-hand side, we have a incompatible communication, or two Go routines, where one Go routines receive and then send the value, but then actually you don't get received. So this is incompatible because, well, I'm expecting someone to receive my message. And you have to trust me on this, but the type system also takes into account of other programming language primitives like loops, if then else, and other control flow primitives. So now that we have a model and we have a way to kind of type check a process calculi, just similar to how you could do with ordinary types, what we need to do next is how do we go from the source code to the model? So what's the relationship between source code and a model? As I said before, you can't just remove lines in the source code to get your model. So we used some techniques in program analysis. So if you're interested in this topic, last year there was a talk by Francis on program analysis, which was really good. And I'm not going to explain too much into that, but all you really need to know is we wanted to extract the session types from the source code. And again, Go's amazing ecosystem of tooling comes to the rescue, because there are a lot of tools that can help us do this, whether it's a dynamic or static analysis. So we look for, given a program source code, we look for the interesting communication primitives like making channels, receiving, sending, select, close, etc. And then we analyze the source code using the Go SSA package. So the Go SSA package is an intermediate representation of the program source code. And well, all you need to know for this talk is that it makes it easier to understand the program control flow. You don't just do an analysis on the syntax. You actually follow the program control flow as well. And so as an example, this is the type. On the right-hand side is the type that we extract from the program. So in main, we make 2 channels, and at the end of the program, at the end of the function, we receive from the two channels. And then similarly, we do it for all the Go routines that we spawn in the program, like sender, the receivers, and also the worker. So notice that the worker, it doesn't do any communication. So when we try to extract the communication types, it's actually just empty. And then now that we have the communication structures of each of the Go routines, we just have to put them together. And so we collected all these Go routines, these session types that we extracted from all of the Go routines. And then we asked the question, well, are these Go routines together compatible? So it's like running the program, except it's not in the program sense. It's just in the model sense. So we combine all these models together to get a bird's eye view of messaging. And we call this global graph because this is globally what your messages flow are like. But the very simple understanding of this process is just you try to find the send and receive on the same channels and try to match them up. And the actual analysis is actually much more involved than what I'm presenting here, but then the idea is just the same. So we have to, so I'm drawing the arrows between the senders and the receivers on the same channels to show you how we match up the senders and receivers. And as you can see, one of the receivers have a receive that doesn't match up with anything. And so this whole model is incompatible. And because this is incompatible, our model says, well, there is a deadlock, which is what we expected. We know that there is a deadlock in this program. And this is how we do our deadlock detection. So, well, I've explained how we do our deadlock detection, and so now I just wanted to conclude on what I've talked about today, which is the process calculi influence the design of concurrency in Go. And we have applied current research on deadlock detection for process calculi in Go. And because Go is such a well-designed language, and also it's very formally founded because it's based on CSP, especially in the concurrency sense. Well, I'm giving this talk with the hope that this can inspire more concurrency research based on Go, because well, what's all the nice thing you can have in a formal model when you cannot use it in a real program, right? And if you're interested in our research, here are some references, and I want to also thank my colleagues, especially my advisor, Nobuko, for working with me on this small project. Don't know if I have more time, but so again, as I've said before, this is still a research project that's ongoing, and currently we support only unbuffered channels, and we've got slightly limited support for dynamic patterns. But don't worry, we're working on a more comprehensive theory and an updated tool, so stay tuned. And if you're interested in seeing a demo, please come to me. I don't think I'll show it now. And thank you very much. Hope you enjoyed the talk.